All right, I thought I'd make a video solution here for test 3 so you guys can kind of self-grade yourself because, as you know, with this online grading, I can't really make comments on it. I can just give you a total score. But also, if I do this now, I think you can get a good idea of what your score is, and then you can go back and look at the average of your 3 tests and decide if the final is worth taking or not here. All right, so let me begin. I printed up the answers. Maybe I thought the easiest thing to do was just to put them out here and let you see them. Maybe I'll go ahead and just write the answers in A, C, A, C, A. 5 is B, 6 is a C, 7 is a D, 8 is a D, and 9 is a D. On the next page, looks like number 10 is a B, 11 is a C, 12 is a D, then an A, and then 14 is a B, 15 is a B, 16 is a B. How far does this go? 17 is a B, and then 18 is a D. And then the last two, multiple choice here, 19 is a B, and 20 is a D. Now, I'll go through them before we get to the free response here, but I thought maybe at first you would just want to be able to see the answers if you just wanted to kind of move on. But I'll mention them here in passing. It says, and you can see this is right from chapter 15. It says, if a cycle begins at a certain position, it ends when the object is. And don't fall for A, the next return to that position, because if you had, something going up and down, let's start in the middle, and if it goes up and then here, that's same position, but it's not going the same direction yet. So it's got to go all the way through a full cycle. So it's got to get back to the same position and, of course, moving in that same direction. I guess another example was if it, you thought about it right here and it went up just a little bit and came back down. Well, that's not a full cycle. It's got to go all the way to the bottom and then come back up to where it had started going in that same position. And so that's why C is the next return to its position while traveling in that same direction would be the best answer here. And A would be an almost correct answer. Okay, also, in fact, these first four are from 15. It says, a mass suspended from a spring is seen to bop up and down over a distance of 20 centimeters from the top to the bottom of its path twice each second. Now, twice each second is about frequency and period, but that's not the question. The question is, what's the amplitude? So, again, if it was going a distance of 20, so it's at the top, it would go to the equilibrium and then back down. That total is 20, so up and down is the 10, so that's why the answer would be A, 10. Changing which of the following affects the period of a pendulum. Now, the equation for the period of the pendulum we didn't exactly work out, but we did say that I would work it out for you in Physics 123 when we've got some calculus and some other mathematics behind us. But we had a whole lab where we were focusing on this equation, and the point was to realize that mass and amplitude did not affect it. It was the length, and so that was that cool little experiment that we did where we changed the length here. 4, if the fundamental frequency of a 2-meter long rope fixed at both ends. Okay, so if I think of this as 2 walls fixed at both ends, the fundamental one is the one where it goes up and then down, representing really a half a wavelength. If the rope was longer, you would see this, which would make a full wavelength. If it was even longer, you would see something out to here, which would be 1.5 wavelengths. But the fundamental one is the lowest frequency one. The one only has one hump in it. And so that's the 2 meters. So the 2 meters here is representing a half wavelength. And so the speed of the wave is, so the speed is the wavelength times the frequency. And the frequency is the easy part. That's the 10 that's given. But it's the wavelength that they want you to really focus on. So the wavelength would be 4 meters because this 2 meters represents just a half a wavelength. And so you multiply that together, you get 40. That's why the answer is A. Now going on to 16 in sound waves, it says sound in waves are, and of course this would be longitudinal waves. We talked about how the wave with like one molecule moves forward, bumps into another, moves forward, bumps into another, moves forward, bumps. And so this one atom keeps going back and forth, and the energy goes in that same direction that the vibrations are. That was the definition of transverse. Of a longitudinal, whereas transverse was when the oscillations were perpendicular to the direction the energy flows. So this was a longitudinal one. And so it's kind of the very first thing we started about in that chapter. Number 6, if we compare the speed of a periodic sound wave with a frequency of 220 hertz to that of a wave with 440 hertz, the 220 is moving at the must be the same speed. This was the lab we did on the speed. We doubled the frequency. Now in lab I think we had about 750, then we doubled it up to 1500. But the whole point was the speed depended upon temperature only. That's what we talked about in class. We even had a nice little formula for it, but it did not depend on the frequency. So that meant if you change the frequency, like in this case from 220 to 240, you increase it, you must decrease the wavelength so the velocity stays the same. Anyways, but all that is saying the same thing. It stays the same because the wavelength corresponds and changes accordingly because the velocity only depends upon temperature. So, and there was no discussion here about temperature, so same temperature. That's why in lab we got the same speed for each of those frequencies. Now, the loudness or the intensity of the sound is related to, and hopefully you said amplitude. The loudness is really how much it pushes on your eardrum, and that's where the movement of these molecules come in. That's the amplitude. The frequency or the rate at which goes back and forth, that also gets recorded. So that is recorded in your brain a little bit differently. That's recorded as the frequency is recorded as the pitch or the tone. So there's two kind of movements going on, how much the amplitude is, and then at what rate does it go back and forth. So we have the loudness, and then we also have the pitch or the tone. 8, a frequency that is blank times the fundamental frequency will be 2 octaves higher. So an octave went up when you doubled the frequency. So to go 2 octaves, we would have to double and then double again. So that's where the 4 comes into play. All right, so there's our sound waves one. Moving on, let's see, that would be 16. So this would be chapter 17. This is our first chapter on light waves. It says, how do the size and the location of your image change as you walk away from a flat mirror? So the flat mirror was the easiest of the mirrors. Basically, we did this one first purposely because the image would be exactly the same size as we proved, and it would be exactly the same distance. So object distance and image distances are the same. So if this is the object distance, DO, and this is the inside of the mirror, and you start walking away, the object distance gets bigger, so your image is going to walk away, of course, in the other direction, away from you, and increasing. So it says in a flat mirror, your image, and then, of course, remains the same size and the same distance. No, but hopefully you can see it here in D. Remains the same size, but moves away from you. So if you're not changing your size, your image won't change its size. But if you're moving your position, the image will change. And that's what's going on here. So that's why D would be the right one here. What type of mirror would you use to produce a magnified image of your face? If you kind of remember that discussion, the concave mirror was the more interesting one. It gave us things that were upside down and smaller, upside down and bigger, and right side up and bigger. Whereas the other mirror, the convex mirror, so I'm standing on this side, was kind of boring. It always gave us an image that was smaller and upright. So I called it the boring mirror because that's all it ever did. But anyways, to make anything bigger, you got to have this one here. You got to have the concave. So there's our mirrors, concave mirror. And so this is part of that first chapter, chapter 17 on optics, where we was looking at the law of reflection. What is the difference between a real image and a virtual image? And so the images are what the light appears to be coming from, or really does come from. And so we said that, and the answer would be C, the light really comes from a real image, and it only appears from a virtual image. So way back here on number 9, I drew this flat mirror. That'd be a virtual one, because the light never went there. The light actually hit the mirror, bounced off, and went that way, but it bounced at such an angle that it appears that the light's coming from back here. So that'd be a virtual one. And so basically any images that is behind the mirror must be virtual, because the light can never really be behind the mirror. But as some of those trick mirrors show us, you might get an image, I'll just do, let's say this forms an image of you upside down and kind of in front of the mirror because the light came and then all met at this point. Well, then the light really is converging there. And so, if the light really appears to come in front of the mirror, it must have really come from in front of the mirror. That's where the light really is. So that's the whole idea of that fancy word, real image versus virtual images. Okay, and I think the last one from this chapter, it says, what type of image is formed when an object is placed at a distance equal to 3 times the focal length of the concave? So maybe if you do a little drawing or remember from the lecture or look on your notes while you're taking the test, this is the focal length and we go 3 times that. So 2, 3, maybe right about here. And we put an object, the light would hit the mirror and bounce off and come over to here and bounce off. And as we said, anytime that you have a concave mirror, the more interesting mirror, you might get one of those 3 situations I talked about. And we got the one where the image was smaller and upside down and in front of the mirror when we were more than 2 focal lengths away. And that's what we are. We're 3 focal lengths away. So this is going to make an image that is upside down. It's going to be smaller. But for this question, it is going to be in front of the mirror, which means it's going to be virtual. It's going to be a real. And so it's got to be real. Oh, and then inverted. Yeah, I guess real and erect would be C. That'd be wrong. But so we've got both here. It's inverted and it's also real. All right, so going on, I think, to our refraction here, so we'll do some lenses stuff here. It says if you are standing at the edge of a swimming pool filled with water, looking at the logo painted on the bottom, the logo will appear to be, so if this is the bottom of the swimming pool, and so here's the water level on top. You're at the edge of the pool right here, looking in. The light's going to come up, and so we get our depth perception, remember, from our binocular vision. I'll exaggerate, and I won't even make the light go to the human eyes so you can see it better. But since the light would go from the slower moving water to the faster moving air, or the light moves faster in air, I should say, and slower in the water, it would bend away from the normal, spreading out. And so the appearance, if these 2 rays were drawn back, and definitely exaggerated, would appear like the logo is right here, where those 2 beams would have traveled in your brain in a straight line. So it didn't really come from there, so it's a virtual image, and it's closer up, and so that's why it appears closer to you. maybe you've experienced. If you've ever stand on the edge of the pool and you look in, you go, how deep is it? And you look in and you go, oh, that's not too deep. That's just 3 feet. So I better not dive. I'll just jump. And you kind of jump and you hit the water and you think you're going to hit the bottom and you go, whoa, 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 whoa. And then you hit the bottom and you're like, wow, that was 4 feet. It looked like 3 feet to me. And this is why. Now, mine's exaggerated, so my 4-foot pool looks more like 1 foot. It's not that different, but it is about a 4 to 3 combination. Okay, so the critical angle for total internal refraction from the air-water interface is approximately 48 degrees, okay? In which of the following situations will total internal reflection occur? Okay, so this discussion about total internal reflection was when you have light coming up, and I'll say from the water, because you have to go from the slow moving light to fast for this to work. Because the fast edge gets out and kind of spins it around and shoots it back in. So you could never be going from fast to slow. You've always got to go from slow to fast. So the incident light must be in the water. So we can rule out the C and D right away on that one. And the critical angle is where the angle was big enough that it had just enough room to turn around. Anything greater than that would even turn around. So it says 48 degrees. So at 48 degrees or greater, so that would be B. Whereas A is not big enough in the angle. On to 15, assuming that the following colors of light pass through a prism, which light wave is bent the most? And so if you saw my little experiment, the violet travels, if this is white light, so it has all the colors, the violet travels the slowest, and it's the change in the speed as you go from air to the prism that's going to bend the most. And so there's going to be some bending and some more bending, and the violet would be the most, the red then would be the least, and all the other colors would be somewhere in between. So what would bend the most would be violet's not an option. Indigo, well, not really an option. Oh, I forgot my blue here. Roy G. Biv. They don't list indigo, but then on this list, then it would be blue. All right, so of all those options, blue would bend the most. For a converging lens, a ray arriving parallel to the optical axis. So here's my lens. We can talk about a focal length. Here's the optical axis. And the whole discussion about this is that a ray would bend and go through this focal point. In fact, all rays would bend and go through the focal point. The middle one, I guess, doesn't bend at all, but goes through the focal point. And the ones on the bottom would now bend upward, and they would all bend and go through the focal point. So B, it would pass through the principal focal point. Yep, right there. 17. And it looks like we're on to the last chapter here, 20. We're going to charge things up. When silk is used to charge glass, the glass obtains, and so maybe I'll draw a little piece of glass, obtains a net positive charge. So the electrons are going to be scraped off. And if this is my silk piece, then the electrons are going to transfer over to the silk piece. So the glass is now positive, the silk would now be negative. Therefore, we know that the silk has a negative. And net negative is not just negative, it's net negative, because the silk is made out of a bunch of atoms, and each atom has protons. So it does have positives in it, but it just has more negatives because it tore them off of the glass and put them onto here. Which of the following objects are attracted by a positive? Okay, so if this is a positive, hopefully you saw and learned both in the lab and the discussion here that a negative would be attracted. That's true. But even a neutral, because in a neutral, what ends up happening is the object itself is made out of positive and negatives. And so a neutral does not mean no charges. There are charges there. And as a result, the negatives are kind of pulled over to what I'll call the front part of the object, leaving behind a positive. And then, of course, the front part of the ball is attracted, but the back side of the ball is repelled. And at first thought, then you go, well, okay, that's still no attraction because one part is attracted, the other part is repelled. However, the attraction here, so if you call this F1 and the other one F2, F1 is a little bit bigger than F2 because it's a little closer. So a positive object would attract a negative. That's the fundamental idea of our electricity. Opposite charges attract. But interesting and maybe a little bit harder to understand is neutral objects are also attracted to positive, which is why the correct answer on the next page, being D, is a neutral and negatively charged objects. Two more here. Suppose you find that an electroscope with its separated foils. Okay, so maybe I'll try to draw the electroscope up here. Ours had kind of this metal knob with a metal can around it, and the metal knob came down and then had a fixed leaf and another one with foil that can then separate out if those two leaves are of the same type. And some electroscopes actually have two foiled leaves. They're a little harder to work with, so we don't have any like that, but it kind of sounds like this is because it says with separated foils and it puts plural. But in our case, we did one had a foil, so separated foil. It says then that they are separated. So you know that these leaves are either both positive or both negative, although you don't know which one. So it says when you bring a negatively charged rod slowly near it. Okay, so if we bring a negative here, that would chase negatives down. Now, if these were already negative, they would become more negative and they would repel out more. But if they were positive, they would be chasing negatives down, would start to neutralize them and they would collapse. Okay. So near it, the foil moves further apart. So they were already negative. And when I chased more negatives down, they got even more negative. That's why they moved further out. So you can conclude that the electroscope is B, negatively charged. And then D, an electroscope is initially neutral. All right, well, maybe I'll draw another electroscope here. Here's kind of that fixed leaf. Here's that movable leaf. Here is the can around the outside of it to keep the wind away and give us a little window we can look inside. But the electroscope is initially uncharged, so the foils our foil is down here. Which of the following would allow you to use a positive charged rod to put a net negative? Okay, so you're going to have a positive rod here, so you're going to have positive. And you want to make that net negative. Now, if you touch it, that won't do it. Because if you take that positive and you touch it, what's going to happen is negatives are going to come off here and go onto your positive object. And so as you pull it away, you essentially sucked off negatives and you would make that positive. So that's a way to make it positive. The way to make it negative is we got to figure out a way to get negatives on there. And that's where that word induction came in. You've got to touch it with something. In the lab, I used my finger. So I took my finger here and I touched it. because what that would do is draw the negatives from my body onto the electroscope. And then if I removed my finger, those negatives would be trapped there. And so even if I pulled this away, in fact, better still, once I pull it away, these negatives that move to the upper part of the electroscope would have no reason to stay there, and they would want to migrate down, and then they would repel each other. So I think everything I talked about was really in D. It says, bring the rod near the electroscope, momentarily touch the electroscope with your hand. Then take the rod away. And so that was the hardest one. I think also the hardest multiple choice question, but it was the hardest one in lab to really understand, and the hardest one probably on the exam here to do. So there's the multiple choice. Like I said, hopefully you did well. Hopefully you graded yourself there, and hopefully you learned one or two new things if you didn't. Let's go on to the free response. And so remember, those are 2 points. The multiple choice were 2 points each. So out of 40 so far, let's look at the other 3 points each for a total of 30 here. So the 40 and the 30 make the 70. And so maybe I'll start working out the solutions here, so that when I finally get done grading the other class, the 122 class, I can jump in on your guys' class here. But take me probably a few more days, so I'm thinking I'll start grading your guys' class Sunday night. Give me Sunday night. The other class is a big class, hard test, so it might take me a while. All right, so let's look at number 21. 21 says that we have a pendulum that is 1.6 meters long. It has a mass of, and it swings with an amplitude of. How much time does it take for one swing? Well, in the multiple choice, I listed this equation. Now let me list it again. And here is the math on it. Actually, I think it stands out better when I write it in red. So maybe I'll, with the red so bright it kind of bleeds through. So let me just rewrite this as period equals to 2 pi times the square root of L over G. And so as we said in the multiple choice, it only depends upon length. So the other numbers in here are misleading, or not misleading as much as unnecessary. And so I won't even pay attention to them. That's just 2 pi times the square root of 1.65 for the length of it, and G is 9.8, and then of course this is meters and meters per second squared. So when you look at the units, the meter is going to cancel, second squared is going to flip up, and then when you take the square root, you're going to get your second. So yeah, the units work out great, and then the time would be 1.65. I would divide that by 9.8. I would then take the square root of all of that. I would then multiply that by a 2 and multiply that by a pi and come up with the 2.59-ish for number 21. And the other one from this chapter, it says, looking at the ocean from a stationary, so you're not moving, cruise ship, you observe the ocean waves. You observe 6 crests that pass you in 1 minute. So I guess that's the frequency, because the frequency is the number per minute. No, I'm sorry, per second, and they give it per minute. So I guess I should be a little careful there. So this comes out to be a frequency of 1/10 of a hertz. That's what that first thing is telling me. And the distance between the crest is 25 meters. Okay, so wavelength is 25 meters. And again, that's what they're indirectly saying. Then they say distance between the crests. So that's the definition of a wavelength. Then it says how much time, would it take for these ocean waves to travel the 4,000 kilometers to Hawaii? Wow, or Hawaii to the West Coast. But to do that, we need speed. So the first thing to do is to remember that velocity is wavelength times the frequency. And so that's going to give us a pretty slow speed of 2.5 meters per second. And then, if you remember that distance is velocity multiplied by time, we could then say time would be distance divided by velocity. So the distance is 4,000, and that's kilometers, so let me put that in meters. And then if I divide that by 2.5 meters per second, you can see that the meters would cancel off and the seconds would flip over, and I would have my answer of how much time, at least in seconds. So 4, 1, 2, 3, 1, 2, 3, divided by 2.5 would be a lot of seconds. So 1, 2, 3, 1, 2, 3. So 1,600,000 seconds. And that's actually good enough. If you wanted to divide it by 60 to get the number of minutes, and divide it by 60 again to get the number of hours, and maybe even divide it by 24 to get the number of days, you would have 18.5 days. So, don't know how realistic those numbers are. I think ocean waves don't take quite that long to cross the ocean, but they do take quite a while. They're not all that fast. But I think it's a week's time, not 2 weeks. But I guess I'm not really sure. All right, but those are our general thing on waves. So that's our chapter 15 stuff. Chapter 16, and I think this is number 23 here. As we get into our sound waves, it says how long is an open, and that's key, pipe organ that has a fundamental frequency. Okay, so one thing we hopefully learned here from the lecture is if you have it open, that's an antinode, and if it's open on the other end, that's another antinode. And the distance from anti-antinode could be, I'll just say L in my diagram, but L could be a half wavelength, could be one wavelength, could be 1.5, but they say fundamental one, so this would be the first one here. So if we can get the wavelength, we can get the length of the pipe. And we can because we know velocity is wavelength times frequency. So wavelength would be velocity divided by frequency. So that'd be kind of the key step here. So since these are sound waves, the velocity is about 340, and I'll take anything. 340 even is fine. I know your author did that. Sometimes they did 345 just to kind of round it off. Usually at room temperature, probably 343 might be a little better, but we really don't know if it's a warmer in that particular room or cool. But I'll just go 343. And then the frequency, what did they say here, was 440. So if I go 343 and divide it by 440, I get a wavelength of about 0.7. It's like I'll round it to 80 meters. And so then if I take half of that, I will get a distance of 39? 35, yeah, 39 meters. Yay. Okay. So there's those two things to put together. And kind of a hard one to understand. In fact, this last part was the definitely the hardest things we've done this semester. And I'm guessing you feel that way. The standing waves is hard. The geometry of our optics is hard. Our electric fields are a little hard. So all those come together here at the end. Although not a surprise at the end. So we've been building up the harder and harder things. So, okay. And let's see, 24. I think I can fit on here. So before I turn the page, let's do the fourth free response. 24 says, what is the wavelength of the musical note of middle C that has this frequency? That's the same formula really we just did. So this one's a little bit easier than that one. It's the first step. So I'll take the 343 again and now divide it by the frequency of middle C, which is 262 hertz. And again, this is meters per second. And this would be a hertz, so per second would cancel, and you'd be left with units of meter. I guess I didn't say that over here, so I'm glad I did here. So put in those numbers, 343 divided by 262, and I get about 131 meters. So a little lower frequency than the one before. Quite a bit lower, actually, which is why the wavelength is quite a bit bigger. And then, of course, the pipe's only half as big also. All right, so there's our, I think, our two on sound waves. Let's move on here to 25. So number 25. And hopefully you heeded my advice in the video lecture that don't try to draw these during the exam, but go ahead and you know, make your note cards. And even in a face-to-face setting, I have students do that because the rays just take quite a bit of time. So it's fun to go through them in class. We'll show you some other techniques when you get more into optics. So having those formulas memorized is really not necessary. So 25 doesn't even need those yet. I'm getting ahead of myself. We won't need that till 26. But 25 is about a mirror. It says a concave mirror has a focal length of 55 centimeters. What is the radius of curvature? Okay, so we learned that the focal point was half the radius of curvature. So if we're looking for the radius of curvature, it would be twice the focal length. The focal length was the 55 centimeters. So if you double that, you get 110 centimeters or 1.10 meters. So that's the first one on our optics. None of the ray diagrams yet. But I think the next three are, if I remember right. An object is placed, here it is, 30 centimeters from a concave mirror and has a focal length of 12. Now I won't go through the whole drawing, but the focal length here of 12. The object is really far away. It's kind of like the one I drew in the multiple choice, where if I took the object, it would go straight and bounce off. Oh, I said I wouldn't draw too much. So let me just stop there. But I would have an image that is smaller and upside down. But what I suggested is that you just make a little note of it. So here it is. Height of the image is to the object as focal length is to object of distance minus focal length. And the other fun little equation was this, the height of the image to the height of the object. Oh, I think we used image and object. I think I'm mixing my two classes here. So let me go image and object. And this was equal to the distance of the image minus the focal length over the focal length. So that was the scenario we worked out first. We had a bunch of different ones, but this was the first and the one we spent the most time on. And so I just kind of looked into the notes and write that down. And our question here in 26 is to find that right here. But to do that, let me start here, because they say the focal length is 12 and the object distance is 30. So I would have a 12 over 18, which divided by 6 makes 2/3. So this ratio here is 2/3. And if you look carefully, that ratio is what needs to go here. So I'll just put 2/3 in for this ratio. then I can solve for what I need. Where is the location of the image? And again, the focal length is 12 and 12. So here I would go 2/3 times 12. Well, 12 divided by 3 is 4 times 2 is 8. And then move the -12 gives me a 20. So a few steps of algebra, but I would get the location of the image location. And 27 is a lot like that. 27, actually it's not quite as hard because it just says, they give us the height of the object. So they have a 3 centimeter tall object. So we don't have to worry about not knowing the ratio and transfer it over. We're going to know the height. The 3 centimeter tall object is 5 centimeters from a convex lens, okay, with a focal length of 8. What is the height of it? Well, again, I won't draw all the rays and do the algebra here. Or maybe I'll draw all the rays, but not all the geometry. But they're saying the focal length, I'm going to make it kind of far out here because they said it's 8, whereas the object is inside of that here. So the ray that would go parallel to the optical axis would bend and go through the principal focal length. And the one that, and I should have drawn my lens a little taller, the one that has this same angle didn't actually come through the focal point, but it has that same angle, would go parallel. And so these two don't meet over here, but they have the appearance of coming from over here. So somebody standing over here would get these two rays and trace it back and say, ah, there's the image. And it would look upright and it would look bigger, and we would call it a virtual image because the light never really came from here. It just appears to come from there. All right, but that was another one we worked out. Actually, we worked it more for the mirrors and then said, hey, this will work for the lenses. So this was the equation. We said height of the image is to the object as the focal length is to the focal length minus the height of the object. And I think that's all we need to do. The second one I don't think is necessary because, like the first problem of optics we just did, we need to do it if we're trying to find this term here, trying to find the location of the image. But we're not. We're just trying to find the height of that one. So I think this is all I need here for 27, because 27 says a focal length of 8, okay, and a position of 5. So this is 8 minus 5, so this becomes 8 over 3. And so 8/3 is what? 2 and 2/3. So you might say that the magnification is 2 and 2/3, because that's what that would mean. But we're asked to find the height of the image, and the height of the object was 3. So 8 over 3. So if I move this over to here, I get 8. So the image height is 8. And like I said, don't even need that second part for the lens. Okay, on to number 28 here. Number 28 says what? An object is placed 10 centimeters from a concave lens. So, okay, so we've got the lens again, and it's concave with a focal length of 5. And then where is the image located? So this sounds like a lot like I just did in 26. I'm going to have to use both formulas, take one and substitute into the other. But I got to make sure I got the right formula. So going back to the lecture notes here, I have the height of the image is to the object. Oh, maybe I should draw a little bit, kind of give us some insight. Here is the lens that is concave, and the focal length was 5. So I'll put 5 on each side, and the object is at 10. And so the light that is going parallel diverges out as if it was coming from that focal point. And the one that was going towards the focal point on the other side of the lens would hit the lens and then go straight. And this was by far the one that was the hardest geometry. If you trace those back, it would look like it's right here. So it would be the boring lens. It would be upside down and smaller, like we talked about that concave one. And that's why it has the same formula as the concave mirror. No, I mean, sorry, the convex mirror and the concave lens have that same formula. And this was what it was. Let me kind of work through. That was the first one, and the other one was height of the image is to the height of the object as the focal length minus the image distance over the focal length. Okay, so if we put in the numbers, we can do the same thing. In this first one, let me just read it again. We have a focal length of 5, okay, and there's a focal length of 5, but we have an object distance of 10. So that is 5 over 15, which is 1/3. So we could say that the magnification is 1/3. That is, it's going to be smaller, and sure enough, it matches my picture. But where that becomes useful is back here, is then this ratio is 1/3. So then I can put in my 5 minus, and there I'm looking for, where is the image on the 5. So when I bring this over to here, this becomes 5/3, and I got 5 minus the image distance. If I bring image distance over to here, and the 5/3 over to here, which maybe I'll write the 5/3 as 1 and 6666666 repeating. Because this would then be a 3 1/3. And all that's in centimeters. And so there's the 3 real hard ones here, where their locations. And now to the last chapter, 20, the electrostatics. It says we have a 3 microcoulomb charge. Maybe I should bring it into the screen in case you forgot what it looks like here. But the 3 microcoulomb charge is 12 centimeters from a 2 microcoulomb charge. Or what is the magnitude of the electrical force on the smaller charge? It wouldn't matter whether it's the smallest or the biggest. Remember Newton's third law, if the 3 puts a force on the 2, then the 2 puts an equal and opposite force on the 3. So we have just one formula to calculate that force, because it doesn't matter whether we're talking about the small one or the big one, the heavy one or the light one, the blue one or the red one. They have the same force on them. It's Newton's third law. So the smaller charge is not really relevant, other than it's saying we'll find a force on one of the charges, and this one, it's which one? Well, the smaller one. Okay, so we'll find it on the 2, but it is the same as the 3. And so what we called Coulomb's law was this. We had Coulomb's constant times the charge of one times the charge of the other divided by the distance squared. Looked a lot like Newton's universal law of gravity that we saw in the first exam. Of course, though, the constant was different. This is a big number, 9 times 10 to the 9th. And the charges instead of the masses are used. And in this case, we've got, this number is so big, we've got to have small charges. And so normally when you charge our electroscopes up and our problems we did in the lab, they're in the small range, the microcoulomb. So that's why it says 3 microcoulomb. And then this is 2 microcoulombs. Now, of course, the thing to watch out for is our units, because this right here is in units of Newton and meters squared over coulomb squared. That's why it was important that I put the charge in as coulombs, so the coulombs in that one and the coulombs in that one would make a coulomb squared, which would cancel off. But it's also why it's important that the denominator be in meters so that we can go meters squared and end up with an answer in newtons. So when they said it was 12 centimeters, I need to put that into my formula as 0.12 and square it. So now I can grab the calculator. 9 times 10 to the 9th times 3 times 10 to the negative 6 times 2 times 10 to the negative 6 divided by 0.12 squared, enter. And so this would be a 3.75 newtons. And so there's the electrical force between those two. And that's the force on the small one, but it's also the force on the big one. Okay, and then the last one, which asks for the electric field, which we learned the electric field was the force divided by the charge. So if you take this formula and divide it by the charge, you get Coulomb's constant times the charge that's making the field divided by r squared. So this very similar calculation. Coulomb's constant is the 9 times 10 to the 9th. The charge, though, here's where we have to go ahead and maybe look in our notes. What was the charge on a proton? 1.602 times 10 to the minus 19. I'll put the units in just a second. And the distance is 0.05, but it's in centimeters. Let me put it in meters, because again, like we did in the problem above, the units for Coulomb's constant is Newton meters squared over Coulomb squared. So that means I need charges in coulombs, so that's why that number I've looked up in coulombs. And I need distance in meters, and since I'm squaring it, it would be meters squared. So the meters squared would cancel off. One of the coulombs would cancel off, and you'd be left with newtons per coulomb, which is the appropriate unit for the electric field. So if I grab my calculator here, I could go 9 times 10 to the 9th times 1.602 times 10 to the negative 19 divided by 0.0005 squared, and hit enter. And looks like we're looking at 0.00577 newtons per coulomb. And so there's the free response ones. All right, hope that was helpful to you.